I said, all right, in this class, we don't need a lot of physics. But just some simple math, you will see the physics. Now we want to learn how to change the basis. This is a very important thing in quantum computing. And usually you just change a few bases. Because that can make your life easier and also make your, you will get more insight and intuition. Okay? So let's start with thinking about this picture. Now you see that I used the 2D plane to draw the 1-qubit space, 0 and 1. This is wrong, right? Because the qubit space, right, which is a C2 space, can have complex coefficient. But on the 2D plane, I don't have. Right? Do you still remember I say for a general state of a qubit is alpha 0 plus beta 1. Alpha and beta can be complex, right? Minus I, for example. Right? This is what dimension, by the way? How many dimension is this space for a qubit? 2. Because you have 2 basis vector. It's 2D, but it has complex coefficient. It's not the table, the 2D on your table. But I have no choice, right? Either I use Bloch sphere or I use this, right? This is easier. So let's just borrow it and I limit myself to only real number. But all the operation still works in the real space. Okay, so that's why this is fake. Okay, a simplified view. It does not correspond to a spin system. It's just a nice illustration. Okay, so now I have a system. I have 0 and 1. And you do see that 0 and 1 are orthogonal, right? In this 2D space. Yeah. I can have another system, another basis. I call this plus and this minus. This is just a name, but it has some meaning. I call it plus and minus. It's because of some reasons. But it's again just a name. You don't need to worry. And this is 45 degrees in this case. But again, in the real space, there's no 45 degrees because you just cannot map into plane. Okay? So I better don't write 45 degrees, but in order to derive the equation, I need to treat it as 45 degrees, right? So let's say I have a vector here. I call it V. This V just hits 1 unit at plus, and it hits 1 over square root 2 and 1 over square root 2 on 0 and 1, right? Now, you don't need to think about qubit. Can you tell me what is, if I use the 0 and 1 basis, right? Now you need to get used to this notation. When I say 0, 1 basis, I mean the basis with the basis vectors 0 and 1. That's it. And in this 2D plane, it's just talking about these two red lines as the coordinate. How do I represent this plus? Just a simple vector, not this plus, sorry. How do I represent this vector V? Great. 1 over square root over 2, 0, plus 1 over square root over 2, 1, right? Good. I want to write it in the column form because I feel it's a waste of time. But of course, there's some reason because we do matrix multiplication, we do this. How do I write it in a column form? 1 over square root of 2, 1 over square root of 2. And we always remind ourselves when we write this, what do you mean by 1 over square root 2? I mean I have 1 over square root 2 unit of 0. I have 1 over square root units of 1. Okay, we need to follow this convention. We need to know what we are talking about, right? How many eggs did you buy? 12. I assume you say 12 eggs, right? What did you buy? 12. 12 what? 12 apple, 12 eggs? Needs to be very clear. You can say 1 or 12, up to you. If your 12 means 12 one egg, then it means also 1 dozen, right? Okay, this is easy. How about in the plus and minus basis? How do you write V? Say again, 0 minus plus 1 plus, right? You have 0 units of negative. You have 1 unit of plus. Very easy, right? How am I going to write in column form? 0, 1. Exactly the same vector have different column representation because we're representing them in different bases. Now later you will find that we keep switching between 0, 1 and plus minus bases. Okay, so you need to be very good. 0 means I have 0 units of negative, and 1 means that I have, but however, I need to, I confuse you. I need to follow my convention. Actually, the first vector needs to be plus. Okay, so I need to rewrite. It's the same. I'm going to write the same thing. The result is the same, but I just swap the half. So this becomes plus. This is minus, so I have 1 unit of plus and 0 unit of minus, right? Then this one I need to change it because I decided to have the first basis vector as plus. Due to some reason you will know later when you learn the gate. So I have 1 unit of plus and 0 units of minus. Is that okay? I know this is a little bit confusing, but it illustrates the fact that you need to have a convention on which one is the first basis vector, right? I messed up just now. Now I decided the first basis vector, I call it plus. It's up to you, you can swap it. But then you keep doing it, you will get the right math. But then I want to be consistent with my future teaching material. That's why I make the plus the first one. Is that okay? Now I want to tell you, I want to ask you, if now I do a measurement, in the 0, 1 basis, okay, I try to measure whether it's 1 or 0. What is the chance that I can get 1 or 0? Someone say 50%, right? I have the 50% to get 0 or 1. Because the probability, both of them equals to 1 over square root 2 square, which is equal to 0.5. Is this okay? So basically, what is the state of this one for me? It's just very uncertain. I just almost say, asking the girl, do you want to do the project with me? 50% yes, 50% no. So what do you mean? Is that, can I sign you up for the class? 100, that's 100% uncertain, right? 50% this way, very uncertain, right? That's right. If both are 50, 0.5, 0.5, then it's 100% uncertain, right? I can say 100% uncertain, right? Now, what if I decided not to do this? I try to measure in the plus minus basis. What do I get?
1%. One is the probability that
1 means 100, right?
100% probability.
100% certain in plus, right? So this is like the state. This is the so-called Heisenberg uncertainty principle, actually. Remember, people keep saying that I try to measure the momentum of the electron. If I can measure 100% accurately, I don't know what is the position of electron. It can be anywhere in the universe. If I know the electron position accurately, I don't know what's the momentum of the electron. It can be any value from zero negative to infinity. This is like this. Position. Every position is a basis state. Okay? We don't talk about quantum mechanics, but now I tell you. The electron at x equals 0 is at the basis state x equals 0. X equal to 0.01 is another basis state, basis vector. So in this space, it is a continuous basis. Okay? The basis state is continuous. When I do measurement, it collapses to one of the basis states. So in principle, the electron is a superposition of all the location, all the states. But when I look at it, it collapses to where I see it. So if I know where it is, then I mean it collapses to x equal to 10, then it collapses to basis state x equal to 10. Okay? Then I do the measurement. But if I do that, the momentum of the electron is another basis system, just like x may be the the location may be this 0 and 1. Here we only have two basis states, but location have infinite amount of basis states. On my table, this point is one basis state. The point on the moon is another basis state. Over the whole universe, I have infinitely number of basis states for the location. Same for the momentum. They can have zero momentum equals 0.001, momentum equals 1 trillion point 1. These are all the basis state of the momentum. And this is, as an example, maybe the momentum is this plus and minus state basis. Yeah. No, so we are talking about not the space that we see, that you have free coordinates, that is a simple space that we live in. We're talking about the physics that where you are for the state, the position of the electron as a state. So the position can be here or here, or it can be a combination, linear combination of on the left and right. So I have two clocks. My water can be on the left or on the right, or it's a linear combination at the left and the right. And each point is a basis state. It's not a physical three-dimensional space. Yeah, but then you can project into a physical three-dimensional space at exactly which location. But each point is a basis. Yeah, very funny, right?
Why just limit it for these two?
No, there are, but the point is that it happened that in physics, the position and momentum are the so-called conjugated pair. So it's just like this plus and minus. They are just exactly they give you the maximum uncertainty if you want to measure them at the same time. Energy and time is another pair. In qubits, like pseudo-conducting qubit, number of Cooper pairs and the phase are conjugated pair. So if you can measure the location of an electron exactly, then you lose all the information about its momentum. Okay? Just like here. When I can measure the plus minus state exactly, I know exactly where you are. You are at plus state. Then I lose all the information about 0 and 1. 50% 0, 50% 1 means I don't have enough information. Do you see that? Similarly, if I rotate this guy to 0, I know exactly it is at 0 in the 0, 1 state basis. I lose all the information about whether it's in plus or minus. So unfortunately, it's not easy. I also don't understand well, I think. The point is you just take it for granted. We do have bases that are really, we call it incompatible with the other. If you measure it accurately in one basis, you will lose the information in another basis. And that is the Heisenberg uncertainty principle.
So I guess fundamental is measurement.
Yeah. Yes.
So kind of explain that a little bit. What does that mean? So
The point is this: when you say measurement, you need to ask yourself, what do you mean by measurement? Just like the girl, I am going to do a measurement. I can ask two things, right? Do you like me? Is one measurement. This is measuring you like me or you don't like me. But I ask her, do you want to do project with me? This is another measurement. But now it's measuring whether you want to do project with me or not. Right? So same as this, like the electron, I want to do a measurement. I will measure the position or measure the momentum. Right? Then we might say, I want to measure the position and momentum at the same time. But Heisenberg uncertainty principle just tell you that you cannot. You cannot measure both of them exactly accurately at the same time. It's just like here, I want to measure this state is a superposition of many basis states. I want to measure whether it's plus or minus. Okay, then you set up an experiment. It will tell you whether it's plus or minus. Or you set an experiment, it will tell you whether it's 0 or 1. But if you can measure accurately in the 0 state, you are going to lose all the information in the plus minus state. Yeah.
well, I get this game, and I remember seeing a symbol there for measurement which had C annotation. And in other lectures, I've seen measurement symbols with different annotations. And I kind of got the impression that that is tied to the basis state, that which base state you're doing the measurement in, whether it's
I forgot, but for IBMQ, the measurement default is in the 0, 1 basis. And later we are going to talk about how do we measure in the plus minus basis by using the 0 and 1 basis measurement. We basically do an Hadamard gate. We are going to prove that they are equivalent. But I forgot how many measurements they have, but I thought it's only one. But the yeah. Okay, yes. Yeah, when people try to depict in their experiment, they do plus minus, just tell you that they measure in the plus minus basis. But in IBMQ, when you set up the circuit, I think it's by default only Z, 0, 1. Okay?
that's just
Because you really need to set up an equipment to do the measurement. So it's not going to rotate the magnetic field or rotate whatever for you. But there's a way that we can do a Hadamard gate, then you will do an equivalent plus minus measurement. Yeah. No question?
Let's say it's the girl you like, she says no. And then later you ask, you want to do the project. And then she says, yes. Now, now you're completely uncertain about if she likes you, right?
That's what I want you guys to think, that why this analogy is not good enough. It does not have uncertainty principle. Because in principle, I can ask her 2 times, do you like me? Either yes or no, it's still certain, right? Do you want to do project with me? Either yes or no, still certain, right? I can get both of them accurately at the same time. So that analogy doesn't work here, up to here. Yeah. Yes. Yeah. But The problem is this, we want to measure it at the same time. Because our goal is that we have a state of the electron. I want to know what is the position and momentum at this moment, at this state. But the problem is no matter how you think, when I try to measure the electron position, I will change its momentum right away. So then later I measure it again. Yes, I can measure the momentum, but that is not the momentum at that point that you want to know. Yeah. Yes. Okay, good. Okay, so think about this uncertainty principle. Okay. Now, but then I think our goal is not just to understand uncertainty principle, right? The most important is how do you change the basis. So here we want to learn the skill of changing basis. So let me again draw another example. I again make this as 0 and 1. Right, 0 and 1, and I still have this plus and minus. With this, I have a vector, let's say at this location, and this vector has half here and square root 3 over 2 here. Okay? And probably some of you already know what is the degree, right? But it doesn't matter, we don't care at this moment. So this is psi, okay? So given, this is gave to you, yeah? You have a vector psi, how do you represent it again in the 0 and 1 basis? Anyone want to tell me? Thank you. Half 0 plus square root 3 over 2 half 1. Again, is this vector normalized? It means does it has a unit length? Because if you do the square of the coefficient, their sum is 1. 1 over 4 plus 3 over 4. Right? It's normalized. Okay? Okay. I want to represent it in the plus and minus basis. Okay? An easy way is that I just need to expand 0 and 1, right, as plus and minus. Okay, so what is 0? If you look at here, right, 0, what is 0? Maybe I just use pen. This 0 is equals to 1 over square root plus 1 over square root minus. Right? You just do some trigonometry, right? If not, I think you probably can see it. Is this okay? Yeah? How about plus? How about 1? What is 1? Well, definitely 1 has a plus component. It also has a minus component. But it is at the negative part, right? Let me show you why. I just extend this one. This one, this is plus, right? Maybe I just draw another figure, right? This is plus. Oh no, this is 1. And I have plus. I have minus. Isn't that this one has an angle to here, has an angle to here, right? So 1 is just equal to 1 over square root 2 plus minus 1 over square root 2 minus. Maybe not very clear, right? Because this is the 1, right? This is 45 degree, right? You project to here, it is but this is negative of the negative, right? This is negative s's. I mean minus positive s's, so this is minus negative s's. So that is minus 1 over square root 2 minus. Yes?
Where does the one?
Yes. Where does this come from? Because I'm talking about 1 unit of here, 1 unit of plus, or of 1. I want to know 1 unit of 1, right? Of the 1 state. It projects to the plus. This is 45 degree. Here is 45, right? So that's why it's 1 over square root 2. Good point. Yeah. I don't draw it well also because of my computer, but go back to do a little bit math, draw it yourself, you will see that. Okay? Yeah. You can do it without normalized, but the point is, I will give you in mono because we deal with normalized stuff. So you would, but for as I said, in the quantum computing, we're going to do normalized basis vector, orthonormal basis, and also normalized vector. So we'll do that. Once you start with normalization, everything will be normalized. So with this, then I can do substitution. Psi equals to half of 0. I just plug in this. Right, this is from equation, I call this 1, 2, 3. Right, this is from equation 2. And then plus square root 3 over 2 times 1 over square root 2 plus minus 1 over square root 2 minus. This is from equation 3. Is that okay? Just substitution. The point is that now it eliminates the 0 and 1. It's just like what you do for your variables, right? With this, then I can represent it as, let me try. I don't need to simplify. I just do this. Plus square root 3. The whole thing, plus half square root 2 minus square root 3 sorry, the writing is not good. Is this okay? So I was you were given the psi in the linear combination of 0 and 1. Now with this one substitution, I get it as a linear combination of plus and minus. This is a fake example, but turn out the result is correct. Because the relationship between this plus and minus to 0 and 1 is exactly the same when you really do a qubit operation. Okay? But don't go too far with this. Do not try to tell people, you know what, plus n 0 has 45 degrees. This is wrong in a qubit. I just use this as an illustration. And later, we are not going to be able to see this figure because this figure does not exist. Okay, you cannot draw the space on a 2D plane. Okay, I keep reminding you, okay? But it's a good way for you to think. Remember this, okay? Do not say that I teach you something wrong. Yeah. No, you cannot do that because the angle in the broad sphere you are trying to measure is still a 3D space angle. But the broad sphere, only the surface makes sense for it. Yeah. So you cannot do that. I don't know, maybe you use the curved surface, maybe you can get something, but try not to do that.
So this can be done.
What do you mean by cannot be done? You mean to get this equation? So later, next one, later I will tell you that you cannot use this to do basis transformation. I will give you the equation later. Okay, but this is just a feeling. Okay, get a feeling first. But remember, don't mess up with the real space. Yeah, question? Yeah, you can say that only the edge of the circle makes sense because it's unit, but do not say it is the same as broad sphere. It's different because we don't have the complex number. And broad sphere actually has simplified something already also. It loses the face, actually. Okay, so do not think about broad sphere. Up to now, all you need to know is how to change the basis. You understand why we have different bases. You don't use this to do any equation, any mathematical operation. You use this just to step back when you get confused about the hyperdimension, right? Like when you try to think about 3D space, you get very confused. The paraboloid, right? Paraboloid, the 3D one. Then you step back. Let me think about the parabola, right? Oh, parabola is like that. Okay, that's why the parabola is is a parabola. It's like that. Right? You think about ellipse. If you forgot, you cannot understand why an ellipsoid behave in a certain way. That is the purpose. Okay? Yeah.
Everything is in phases, plus and minus.
Yeah. Yeah.
It's
But
not just completely, shouldn't do.
it's not wrong, but it's useless for us because now you try to have three bases plus 0 and 1. They are not orthogonal. Good point. Yeah.